So what I'm going to talk about a little bit is an overview of where I come from, what I do in terms of my research, so to sort of help people understand a little bit more about what I am about. So thought I'd give you a little bit of a biography. Was born in Boston in the U.S. I did my PhD in philosophy, so for those of you who want to see contact between the humanities and the sciences, I guess I'm a good person. I will say that I often tell my students how much I benefited from my philosophy background. So I don't use necessarily my philosophy background in my research, but the preparation that I had in terms of logical and critical thinking, and in particular in terms of writing, is incredibly important. So I always remind people about that. So because of some experiences, I actually had a very good friend in my undergraduate years who developed schizophrenia while we were students. And this sort of turned my interest towards psychology. And I began to take some background courses and steered in that direction. And I think many of you might know that programs in psychology, even if you want to be a clinical psychologist, in North America and I think to some degree here in France, you need a research component to your studies. So I began to work in a laboratory that actually studied schizophrenia. In the beginning, I thought that all I cared about was doing this research project so that I could then become a clinician and that I didn't care about research at all. And in fact, I actually became fascinated, and I really discovered that I enjoyed the process of scientific research. And so I gradually steered more in that direction. I was very fortunate to go to Montreal to do my PhD in clinical neuropsychology. And one of the things that I became interested there, and maybe this is that classic story of how chance can influence your career. I was doing some studies on people listening to and engaging with musical rhythms, and what I saw was a strong implication of motor regions of the brain when people were experiencing these rhythms, and I became really interested in how the auditory and the motor systems interact. So I've been a professor of psychology since 2000, and I just finished 6 years as head of my department. Yay! So I am extremely happy to be here on my sabbatical. And the goals for my fellowship are to develop some new collaborations with people that I already know here in Marseille, to advance my knowledge of some new techniques, and to work on things that I haven't had a chance to work on while I was the chair of the department. And I have a fun new project, which is I want to do some different writing. I'm tired of only writing about scientific things, so I'm going to be starting a little blog about cooking. I'll let you know more. Probably some of you can give me advice. So that is my little biography. And then maybe I'll tell you a little bit more about what I do. So I think for a lot of you in this room, who aren't coming from an experimental science background. I think there are a number of people who are scientists and social scientists. What I do broadly is in the category of what's called cognitive neuroscience. So what is cognitive neuroscience? It's really trying to look at the brain mechanisms that underlie thinking and behavior. So in other words, brain mechanisms underlying what makes us human. So it's things like memory, it's attention, it can be emotion, it can be planning. All of those processes come under the umbrella of cognitive neuroscience. And the key factor is that what we are interested in is what are the brain mechanisms that make that possible, and how do these mechanisms actually work? on the one hand, that can help us understand the brain, but on the other hand, that can also help us understand more about how we think. One of the tools, or a set of tools that I use and that Robert will tell you guys a little bit more about, are brain imaging tools. So I think probably, has anybody in this room had an MRI scan for your back, right? Or an elbow or something else, right? But we can use those tools, those MRI scans, to also look at the brain. And we can look at two parts of, or two aspects. We can look at both the anatomy, just how the brain is put together, and we can also look at how the brain functions. So probably any of you who've read stories about brains, cognitive science in the popular press have seen these beautiful images, color-coded images of parts of the brain lighting up when you engage in particular tasks. So as I said, what I became particularly interested in is complex motor learning, integration of auditory information and motor response, and especially in the context of music and dance. I've done less work on dance, but that's something that I really enjoy, and it's something that I also have a couple of colleagues here who are interested in. So music engages all of these kinds of cognitive processes that I talked about, right? It engages memory. It requires focused attention. It requires complex motor behavior. So studying the brain mechanisms underlying perceiving and producing music can give us a window into both how the brain works and into music. So sometimes it's the case that not only do we discover something about how the brain works by studying the brain, by studying how the brain processes music, but sometimes we also discover something about music itself, which is really fun. I'll just say, because there are a lot of scholars from a lot of different domains in this room, that of course cognitive neuroscience is only one approach to the study of how we engage with music. We work alongside with people from traditional psychology. We work actually quite a bit with people who are musicologists, music theorists, so people who understand how music is engaged with and processed across cultures, people who understand how music is constructed. So for those of you who might do language, it's kind of like working with people who are in linguistics. We do a lot of talking and discussion with colleagues of ours who work with animals, understanding animal cognition and possible precursors of music perception in animals. We work with people from music technology. We work with people from anthropology. So I think the other thing that, the message that I want to get across is this is one perspective on music. It's not the only perspective, and I don't consider it to be the only perspective. So why would you want to use, and I think I've kind of given you a hint already, why would you want to study music if you're a neuroscientist, right? When we think about neuroscience, we think about something like understanding how visual representations work in the brain, or how I make a reaching movement, or maybe even things like how I respond to scary stimuli, things like that, right? So why would we want to study music? Well, one of the big reasons that we want to study music is that it's an extremely complex system for communication, for evoking emotion, similar in some ways to language. So it gives us a parallel which has, again, similarities and differences, so that we can, again, probe a bit more how the brain engages in these types of systems. There are also people who study mathematics from a cognitive neuroscience point of view. And again, the idea is that you're taking a system that is very common to humans and using it to probe how the brain works. One of the other reasons it's really interesting to look at music is it's likely unique to humans. As I said, we engage quite a lot with and are very interested in our colleagues who look for similar processes that might exist in animals, but probably music as we understand it is unique to humans. It's ubiquitous across cultures. There are no known cultures that don't have some form of music. We, from our culture, may be more or less able to understand or engage with the music of a very different culture, but all cultures seem to have music. And the other thing that I think is really important is that most people spontaneously produce or engage with music. They don't require instruction. Often, I think in Western culture, contemporary Western culture, when we think of music production in particular, we think of experts, we think of Yo-Yo Ma, we think of highly trained musicians. But in reality, all of us, in some senses, are musicians. We have the capacity to engage with music. And this, again, makes it similar and very interesting, like something like language. There seems to be a system in place that you don't require external training in order to evoke, at least in a very basic form. So, that's the why. So I'm showing you this picture. This comes from a review that Robert and I wrote with one of our fantastic students a few years ago. And this is kind of telling you what it is that our project is about. So if you look at this person who is, we're going to say, a fabulous violinist who's playing a beautiful tune, what we want to know is all the different kind of brain mechanisms that make that possible, right? So you have the fine motor control that allows that person to produce the sound. They have to listen to what they're producing and monitor it and make sure they're producing what they want, right? So a violinist is always trying to fine-tune to evoke the emotion that you're going to experience when you listen to that person. There's planning, there's memory, there's all kinds of processes. So this is what we want to know about. In my lab, there's sort of three big projects that I'm working on right now, or sets of studies. I'm very interested in musical rhythm and what we call musical groove. I'm interested in how people learn, so people who don't necessarily know how to play music learn to play, or learn something even simpler, like basic components of music. And I'm also interested in looking at people who are trained musicians, who are experts. So in terms of rhythm and groove, one of the reasons why this is interesting is because there seems to be a strong and almost obligatory link between sound and action. People move spontaneously and effortlessly to music. All you need to do is probably check into your Facebook page if you have any friends with small children, or go to YouTube, and you can find a million videos of like 2-year-olds going, right, to music. This, again, it doesn't require any instruction, and you can also find any video of a concert, jazz concert, classical concert, rock concert, where people are bobbing, snapping their fingers, tapping their feet. And we know that musicians who are playing together typically use those movements to stay in time with each other, right? So movement and sound seem to be automatically linked. One of the things that we found with our student Joyce is we did a study where we had people listen to musical rhythms. And they were just lying still. They were in one of these brain scanners. They were told they didn't have to do anything. They just had to listen attentively. We were going to ask them something about them later on. And when we looked at the regions of the brain that were active when they were just listening to these rhythms, we saw a strong activity in motor regions of the brain. So just listening to a rhythm, even if you don't intend to bob your head or snap your fingers, engages the motor system. One of the phenomenon related to this that we've been looking at lately is what's called musical groove. And I've been doing this in collaboration with one of my students and a fantastic collaborator who's now in the UK, Maria Vitek. And groove is something that I think that we've all experienced. This is this feeling, right, where you hear a particular type of music that you enjoy that has a relatively strong beat, and you just feel like moving along. So I'm going to give you an example. One of my students is in a Brazilian drumming band, and I think this and this will just get us woken up this morning. So I hope we're going to hear this. Yeah, I have a feeling the HDMI is stealing the sound. So I don't think we're going to hear this, but trust me, if you could. One of the advantages of studying music neuroscience is that you get to have students in your lab who do all kinds of amazing stuff. Okay, so the next part of what we do is to look at how people learn musical skills. And we, of course, know that if you practice, if you learn to play the guitar, if you learn to play the piano, your behavior is going to change, right? You're hopefully going to improve in terms of your ability. And some people will improve, more than others. There are individual differences. But underneath all of that, of course, learning to play something also changes your brain. And it can change it in terms of both the structure, so how the actual wiring of the brain is put together, and in terms of how those connections are used when you're playing. One of the really fun ways that we do this, and this is in collaboration with Robert and also with a person in music technology, is that the student in music tech actually built for us devices, so a cello-like device and a piano-like device that you can play inside this MRI scanner. Because you can't put a normal instrument in there. As any of you know, it's really quite small. And because it has a strong magnetic field, you can't use a usual instrument in it. So this is among the really kind of fun things that we get to do. And then we can take people. So for example, Indiana, who's a student who came to us from Paris, she and one of her fellow students, who are both cello players, trained non-cellists, people who had never played an instrument before, to play the cello over 6 weeks. And we were able to track the changes in their brain activity and their brain structure as they learned to play this instrument in a very limited way. Of course, these people didn't become professionals, and they were playing actually quite a difficult, the cello-like instrument is not all that easy to play. But still, we were able to look at what kind of changes were induced in their brain. So the last thing that I'll talk about is long-term practice, and what we talk about is expertise, or what happens when you've trained for a very long time. So you are a well-trained pianist, you're a well-trained violinist, or you're a well-trained dancer. So long-term practice, and most of the people that we study will have practiced for something like 15 years at least. So they're either students, high-level students in music programs, or they're actually professional musicians. And what you can see is that people who have trained for these very long periods of time have differences in their auditory, motor, and other kinds of cognitive or attention, memory kinds of regions of the brain. And one of the things that is particularly interesting is that training that starts very early in childhood, so if you start before age 7, produces particularly strong effects in terms of people's behavior and these changes in the brain. I'll quickly say that we do not believe that this means that people who start before age 7 are necessarily better musicians, right? There are many, many things that go into being a musician, and we can think of a lot of really salient examples of people who are excellent musicians who started much later. So Jimi Hendrix didn't start playing the guitar until he was 13. Aaron Copland didn't start playing the piano until he was much older. So there are lots of examples. But in terms of my question, right, which is understanding how the brain works, what it's telling me is that at certain points in development, very likely when the brain is changing rapidly, if you get a specific kind of experience, you're going to produce greater changes in the brain. And of course, it depends on the kind of experience you get. Not all experiences are similar. So I think a lot of us who speak a second language know that because we learned our second language later in life, we'll always have an accent, right? Whereas people who start their training in their second language earlier in childhood typically have much less of an accent and also have more facility with some of the very fine details of grammar. So these effects of childhood training aren't necessarily everywhere in the brain. They're specific to the training that you're getting. So for example, in our early trained musicians, we see changes in higher level motor areas that are probably about linking sounds to actions. So what are my next steps? Well, I'm here in Marseille. More groove. So we want to look with a collaborator here at whether our brain waves, so you can also measure the electrical activity in your brain, whether your brain waves actually synchronize or go in step with the beat of music. There's some evidence that this is the case. And to do that, one of my students from the lab is actually arriving next week, and he's going to be staying for a couple of weeks to help develop the project here. And the other thing that I've been doing some work on and I'm interested in developing further is looking at the question of whether or not musical training can promote different aspects of language learning. So there is some evidence that this may be true. So there may be, it may be the case that musical training actually tunes or trains particular aspects of this auditory-motor integration that are actually also relevant for language. And in particular, there's a number of larger studies going on. There's a group in Lyon who's interested in this, and groups in the United States who are interested in the question of whether or not some type of musical training, even if it's not that you're learning to play the violin, but some type of musical exposure, engagement with music, can be helpful for people with language and reading problems. So I will just say thank you. I'll show you a little picture of all of my lab. Some of the pictures look a lot like it could be here in Marseille, and other ones we're doing Canada-specific snow activities. So I'll just say thank you to them, and I'll really say many thanks to IMéRA, to ILCB, who are the university side that is welcoming me, and to the University Aix-Marseille in general.
Thank you very much.
Good.
We have time for 2 questions, short questions. Please,
Very interesting. Now, I'm a scientist, so I'm interested in one thing. So, suppose that you have a musician who starts training from a very early age and develops these structures in the brain, as you pointed out, how does offer any insight on the matter?
So I think when you talk about something like reasoning, right? So reasoning is a very high-level process that comprises a whole lot of other steps, probably including training. So if you think about, so maybe what I'm going to say is, don't think about reasoning as a single lump, right? There's scientific reasoning, which you and I have been trained in, but there's musical reasoning, which musicians have been trained in, right? So I don't think reasoning is a single category. I can't reason about music because I don't understand, I'm not knowledgeable about musical structure. I can't think about how to use musical structure to convey emotion, whereas I can think about how to use scientific method to answer a question. So I think it's a red herring to think that reasoning is just one thing.
Okay. Keep the question. You will have the opportunity to talk to her.
You can pester the life out of me later.
Just keep the question short, and then Nusa and
No, okay.
you're okay. So Nusa and I think that Andy wants to ask. Yeah, Nusa.
Yes,
Yes.
thank you very much. It's really fascinating. I have two short questions.
Excellent.
First is, does it apply to singing? If we consider that the voice is such an instrument of music. Third question. Second question, it makes me think about using music for some neurodegenerative diseases. So, what kind of things are you working on,
Yeah.
or could you tell us about?
So the first question is a really great question, and in fact, we used that fMRI-compatible cello to compare the brain networks that are important for singing and for cello playing, because one of the things about singing is, of course, that you have to control this very elaborate vocal system, and it's a continuous pitch. You can have any pitch you want. So it's similar to the cello. So what we think is, yes, there are overlaps between the system for singing and the systems for playing music, but there are also specialized systems for singing. In terms of neurodegenerative diseases, yeah, there are a lot of people who are interested in this. It's not specifically what I do, although I have done one study where we used musical training in the context of stroke. So trying to help people use a little piano to regain motor function. But there are people who are interested in Parkinson's disease. There are people who are interested in Alzheimer's disease. There's a lot of interest in trying to use what we now have learned to engage with these things.
Andy, last question.
Look at elephants. There's huge sexual asymmetries in the amount of vocalizations that males and females do. Females are
In what?
elephants.
Elephants. Great.
There's a specialist in elephants.
Really?
Really?
I love elephants.
Yes. Female elephants have 40 different vocalizations that have been recognized. Males have 5 with basic male functions. Do you see any sexual asymmetry in the ability to learn music between males and females?
That is so interesting. I did not know about sexual dimorphism in elephants. Typically what we will do in our studies is we will try to balance the number of males and females that we have. And I am not aware of sexual differences in terms of the ability to learn any of the skills that we've seen. This doesn't mean that they couldn't be there. There's been a long and sort of fraught history of looking for sexual differences in cognition in human neuroscience, and the few differences that are there seem to be quite fragile. There may be differences that creep into music performance because of choice of instruments. So you very often see not so many female brass players because of lung capacity or large instruments or things like that. Large hands is super helpful for playing a lot of instruments, so you might see, but in terms of actual ability to learn, I'm not aware of it, but now I want to know all about elephants.
Thank you very much.